I would like to introduce Gian Michele from MIT. He received his PhD from the University of Turin. He worked in Alice, and then he went to MIT to join the heavy ion group as a postdoc. Then he got a research scientist position at CERN, working in Alice there. Right?
Very inefficient use of people's time moving back and forth.
All right. But now he's back to MIT working in CMS as an assistant professor. So please.
Thanks a lot, and thanks for inviting me. Yes, so today I hope that you can see the slide fine. I'm going to talk about LHC as a photon-nucleus machine with the idea of studying called the nuclear matter. So this presentation is meant to be for non-heavy ion expert in a way, so I'm happy to tune it up a bit if you find it that is too trivial. But yeah, okay. So the basic idea is that, of course, we work in heavy ion at the LHC, so, and heavy ion is a large hadron collider is a proton-nucleus and nucleus machine. We accelerate ions and protons, and now also light ions at ultra-relativity speed. And I mean, this is usually what I also use for undergraduate students. So that's the type of object that we collide. Those are very early Lorentz contracted objects that lead is, as you know, 82 protons and in total 208 of total mass. The question is, of course, if we deal with the hadronic collision where the photonuclear and where the photons are coming from. And the main point is that once we have somehow a biased picture of what colliding ions means in a way, at least I had before I got into UPC physics. So effectively, once we collide ultra-relativistic ions, as we know very well from electromagnetism, there is this famous approximation that tells us that Lorentz contracted electromagnetic field can be pictured as a field of a cloud of virtual photons. In our case, this was an old-standing hypothesis and description that comes from Fermi, and then was updated for a case of ultra-relativistic ions by Stacker and Williams. So indeed, what happens is that if we now think about how heavy ion collision happens, instead of having a bunch of ions colliding with another bunch of ions, this is a very dummy visualization of how it's probably slightly more realistic to picture heavy ion collision. So effectively, as you know, it's extremely difficult to squeeze many ions in the same bunch. This is because there is a very high repulsion, electromagnetic Coulomb-like repulsion between them. So, and on the other end, of course, a strong force is a short distance force, but the electromagnetic interaction is a long distance one. So whenever you combine two bunches, most of the time, you are colliding not ion with ions, but photons with the ions or photon with photon. Just to give you an order of magnitude, at the LHC, we have these days order of 50 kilohertz of lead interaction, so 50,000 interaction per second. Here, when we consider the full electromagnetic cross-section, we are dealing with the order of 10 megahertz of soft photon-induced interaction. So in a way, LHC, when we collide ions, we are already running a photon nucleus or a photon-photon machine. So this is where, of course, this is not a new idea, but people have tried for a long time to use ultra-peripheral collision. The picture is simple. These are collisions in which, in a, let's say, geometrical, classic manner, the impact parameter of the two collisions is larger than the sum of the two nuclei radii. And the good somehow side effect of this fact is that when colliding collisions of ions, we have a unique source of high energy photon nucleus collision that can be, of course, used to study the properties of nuclear matter. And I mean, as I will mention later on, in the US, we are now working hard to get an electron-ion collider, which of course has advantages, but still, even with the electron-ion collider, this will still be the highest, the largest and more abundant source of high-energy photon-nuclear collision. So it's definitely a very, very important source. I think that is funny because when we started the LHC, these were basically background events. So we were just trying to get rid of them. And now over time, we are learning how to make a good use of them. So before going into the discussion of the UPC, I just wanted to spend one second to remind ourselves about how we can measure the properties of quarks and gluon in protons and in nuclei. So the classic observable and the classic process is, of course, scattering of point-like particle on protons. Of course, if you want to study the structure of an object, you do not want to get started with a very complicated probe. So, and the simplest things, and this was what has been exploited so far at ERA in electron-proton collision, is of course scattering an electrons on a protons, tagging the outcoming direction of the electrons that give you control of the full kinematics of the scattering. And in this case, you have a full control of the dynamic of the system. And in particular, we have learned how to describe the properties of nuclear matter through basically two quantities, the virtuality of the photon that gives us the spatial resolution of our quote-unquote microscope, and then a Bjorken-x that is related to the fraction of the momentum, longitudinal momentum that is carried by the parton that would scatter on. So what we have learned over time is to codify this information in parton distribution functions. Of course, that tells us the properties and densities of constituents, quarks and gluon, as a function of x and q squared. And this is, of course, something that is deeply non-perturbative. So we have learned how to describe it. And in a way, parton distribution function as fragmentation function encodes all what we do not know. So this is, let's say, the classic, and we have explored a proton PDF in electron-proton collision. Not much we know yet about nuclear NPDF, at least from a photon-induced collision. And of course, one of the objectives of this field is to characterize how the properties of matter that we usually plot as a function of Bjorken-x and q squared evolve when we go from a low density limit. So basically, when we can picture the proton as a simple structure of a valence quark into the low Bjorken-x region. And what we know is that as with a big lab evolution, when we have a Lorentz contracted ultra-relativistic protons, effectively we have splitting. So IX quark will start radiating, and then higher IX gluon will start radiating lower X gluon. This will basically start populating more and more the structure of the proton or of the ion, and it is a long-standing trivial prediction in a way that this increase cannot go forever. Now, whether you frame it as a what is called color glass condensate or not, there is something very simple. The scattering amplitude cannot become infinite. So the number of gluons that you can have cannot diverge. And this we know because when we do a cross-section measurement, where the probability is finite. So no matter what is your favorite description of this low X increase, there must be within QCD a way in which this divergent behavior gets controlled. And now indeed we get into the field of modeling or calculation within QCD. There has been a lot of effort in trying to describe this low X region. What is predicted is that if you go to the very, very low X, so here we are sensitive to, we are being sensitive mostly to very low X gluon, so very soft gluon that come from a shower of splitting. We should expect at some point that there are processes that counterbalance this increase of gluon density, and one way to regulate this divergence is to have processes of gluon merging. What I want to stress is that despite the fact that when you go to modeling, this become, of course, a phenomenology in a way, having evidence of this would be a substantial improvement in the way in which we describe QCD. This is when we are talking about splitting, we are in a linear regime. When we talk about gluon merging, we are basically experiencing non-linear evolution of splitting function. So having any indication of this regime would be extremely valuable. And in addition, I want to say, even if we don't go to the saturation, there is still a lot of unknown about NPDF in proton, in particular in lead, even when we stay in the region of 10 to the minus 3 or 10 to the minus 2, where we are not expected to see non-linear effect.
Do you mind if I interrupt you with something really stupid question? So you talk about this gluon merging as an idea, like, why isn't it naturally there with just some ideas of time reversal, that if I split, I can merge?
So I think that so you're asking why it's not obvious that this should happen? Or
that seemed to be what you were saying, is like, okay, it's been hypothesized, and I understand the arguments about the non-linearity, but if a gluon can go to 2 glues and I time reverse, isn't that 2 glue go into 1?
I think that this is not, this is not new physics in a way, but on the other end, this is basically beyond collinear factorization.
Okay.
So that's a way to see it. So I think that if I have to see it from the outside, there must be somewhere the need of phenomena that are not linear in order to prevent the total cross-section to explode.
Okay.
And that's what we would like to see, and we would like to see, of course, where it happens. But hopefully, is within the range that we can access. But when it happens, at which density it happens, that's also part of what we would like to know. So where is the business of nuclei versus protons gets together? And by the way, this is a topic that is very, very sensitive for many people. So the original idea is to say, okay, if we go for lead, we start from a higher initial density because you are Lorentz contracted. I have to say that, and there is also this floating argument of the a to the power of 2/3 that I think is proven, is known to be a very, very rough approximation. On the other hand, there are some geometrical reasons why you might think you go to lead, you just get at higher x to the same regime of low x. Then, of course, something that is not trivial, if we could have, why do we want to use ions when we can use protons at higher energy? Well, the reason is that it costs less. Okay, if I had to get to the same region density in protons, well, I would have to build a machine that is much more expensive, and accelerating electrons in particular is very, very, very problematic. So long story short, this is a simple prediction. There is a very simple scaling that comes from, for example, from CGC. As an experimentalist, I think that this is something that is clearly interesting. We want to measure it, and then we will figure out what comes out of it. So as I say, there are pretty much a lot of data on electron-proton collision from deep inelastic scattering from Zeus and ERA in general ERA, but there is nothing really constraining from electron ion. So this is actually a plot that is in this nice collection of NPDF. It shows us what we know about nuclear NPDF. And what you can see, these are mostly fixed target experiment. So we go from 10 to the minus 2 to roughly 1. And the Q² region that we are actually covering, it goes pretty low. So these are mostly fixed target experiment. But what you can see is that we are still pretty far from having access to the high density regime that we expect to pop up around 10 to the minus 3. Clearly, what is complicated is that why we couldn't do it yet? Well, because accelerating electrons is very expensive. You waste a lot of energy in synchrotron radiation. And of course, in order to address this more quantitatively, we have a big program that at the Electron Ion Collider at BNL is expected to address this physics with the Electron Ion Collider. Again, as I said, still the low X reach of EIC will be lower than the one that we can obtain now in UPC. So in order to, okay, we will of course all be involved in the EIC, but I want to show you here that we have now all the new observable that allows us to do already a pretty good job with ultra-peripheral heavy ion collisions. And again, the picture that I have in mind is the one that I tried to explain before. So why the rate is so abundant? Well, what we know is that this yield of photons scales with z squared. So we have a larger, the heavier the ion you have, and the largest will be the rate of photonuclear interaction. And the second trivial is that in a way here we are cheating a little bit, because we are accelerating a charged object, ions that would of course radiate less, and then we are using this parasitic flux of photon in order to have high energy photon-nuclear collision. And just to give you an order of magnitude, the energy that we can reach in photonuclear collision at the LHC gets up to the order of 10 over 50, 100, and other 200 GeV, depending on how well, depending on the final state kinematic. So one thing that is still important to notice is that these two processes, no matter what is the final state that you are looking at, are still fundamentally different. Okay, so and in particular, the main difference is that in this case, I have full control of the virtuality of the photon. So I'm tagging the electron, and therefore I can change the virtuality of the system and scan it systematically. Of course, what we are doing here is that, by the way, the photon might also probably better it should come from here, because this is indeed a cloud. So there is much less control on the energy of the scattering. So in order to have, these are mostly coherently produced by the nuclei. So the virtuality is reasonably small. So this is clearly photon. This is in the regime of where we do not have full control of the kinematic. What we have to do is we have to maximize the control on the final state in order to have a good understanding what is the transverse scale that we are hitting. But I think that this slide is important because it shows us, let's say, what are the pro and con of the two type of experimental approach. So if you are in heavy ion, you are of course aware of what are the observables that so far have been more systematically exploited in terms of UPC collision. And I just wanted to show you, this is the study of vector method exclusive photoproduction. The picture is pretty beautiful. So you have a photon scattering with a nucleus, and you can picture this photon as a QQ bar pair that traverses the nucleus. And what we expect is that if you look at a final state like J psi, the nucleus, the photon will interact coherently with the nucleus through some kind of non-trivial, at least two gluon exchange at leading order. So what is the beauty of this picture is, first of all, these events have no final state apart from the J psi. So you do not have any kind of final state interaction, hadronization, modification, etc. And also if you use, for example, forward detector that allow you to go to very low X. Okay, so this is a very powerful tool. So I don't have the time to describe all the results that we have obtained in CMS and ALICE and in many other in Atlas, but I just wanted to tell you what are the challenges of this piece.
I'm so sorry. Why do you need why do you need the two gluon exchange in the previous one in the T diagram? I think in my head I only saw one gluon, right?
That's a good point, because these are indeed two different processes.
I see. Okay.
So this is I will talk about this later.
Okay, sorry.
This is effectively a leading order hard photonuclear scattering. Mm-hmm. So is a 1 to 1 to 2 body scattering. This would create a digest. event.
Ah, okay.
That's a very good point, and I think this is probably slightly
Sorry.
confusing. No, that's a very good question. Instead, here what you have is that the photons scatter with the nucleus coherently, and the only thing that gets produced is a J psi. Okay, and you would need, of course, to have a two gluon coupling with the nucleus in order to have a reasonable description. But so the first problem that we have here is that if you think about, there is only one scale in this process, which is the mass of the J psi. In order to find out coherent interaction, we select J psi with very low PT. So effectively, there is only one scale. So the only chance that you have to change the scale at which to test the nuclear matter is to change the mass of the vector meson. And indeed, that's why we are what we try to do using, for example, upsilon or a phi meson. There is also something that over the last year has become even a more problematic aspect, which is J psi are complicated objects. So, and we also have gotten burned one time at least in heavy ion with J psi, because they are in principle simple. But you can imagine that if this is already a leading order description, quote unquote, going beyond that becomes even more complicated. So in the field, we have tried to, there have been a lot of effort in trying to discriminate, for example, shadowing scenario, which are linear between collinear factorization approach and nonlinear scenario that are shadowing. But somehow the fact that we do not have a lot of control on the theoretical description made our conclusion still a bit weak. So while there is a lot of work on this exclusive photoproduction, something that we have started recently at MIT is a program to study hard photoproduction. And here, indeed, the main difference is that here we are not looking at final state events in which there is only one object, but we are really making a digest event. So typically, this would be photon gluon scattering that would give to a jet back-to-back jet topology. So, and in particular, here, one thing that can be useful is that if you start by looking at final state in which you have a heavy quark, then your description becomes much simpler, both at leading, but also at next to leading order. So effectively, this is a CC bar back-to-back production at leading order. So in one sense, it still preserved the beauty of photonuclear. So there is not a lot of activity around, very limited, much lower flow and whatsoever. And also the second thing is that if we do it right, also from the theory point of view, we have a probe that can already be described at next to leading order because we have all the tools from the description of charm and beauty production in proton-proton collision that have been super exploited and optimized over the last 10, 15 years. Now, so this is what we wanted to try to do. And then we had to face the problem that, of course, CMS is not a photonuclear experiment. Okay, first of all, as we know from what from our EIC efforts, typically electron-proton experiments are asymmetric because there is the need of tagging the electrons. There is a different requirement in terms of calorimetry from one on the other. And there are also many challenges related to the triggering, as I will discuss before. But okay, the good things of CMS is that is a wide acceptance detector, and acceptance is key in this measurement. There is charge hadron reconstruction, photon, muons, and there is a pretty good pseudo-rapidity acceptance and PT acceptance. So this is where we got started, and this is a program that we started in late 2023. And the second question is how can we select this type of events? So this is indeed a photon scattering with a gluon. Well, the first thing that one can do is to use the ZDC detector in order to ask whether select the nucleus that breaks, and the nucleus breaks, and it will produce neutrons that we can detect in the ZDC. And then we can ask, for example, that the other nucleus stays unbroken. And this is a way to identify the photon. And then we have experimentally, of course, the possibility of reconstructing a dye-jet or a heavy flavor object in the barrel using the central tracking detectors. And something that I think is quite impressive is that CMS was not designed to be a low PT detector. So it's mostly, despite what Alice, what was the design of Alice, that was clearly always focused for the low PT. Here, CMS was tuned to have ideal performances at the IPT, Z boson mass, and X. But what we could do is that since the occupancy of this event are very low, we are talking about 50 tracks, 50 tracks, 60 track max. So we could actually release the tracking constraint of CMS, and we could actually get very good coverage in PT down to low PT. And we have still 4 or 5 units of pseudo rapidity that allows us to do a very good job in tracking down in a wide region of a kinematic region. So something that I don't know if you are, for those that are not aware and not familiar with the UPC analysis, one of the key aspects is to apply what we call rapidity gaps, okay? And the concept is that what you can imagine is that you would have a huge amount of photonuclear events, lower rate if you start requiring a D0, but as soon as you start to ask for some activity, some R scale in the detector, well, you increase the chance of getting contamination from hadronic collision. So you can have events that, for inefficiency of the ZDC, for example, do not trigger a neutron, but you still have a decent contamination that comes from very, very peripheral or diffractive hadronic events. And what we did is to use a pretty classic gap condition. So we have tried to look at the activity in the forward detector. In the HF, this is a calorimeter that is placed in a pseudo rapidity region that goes from -3 to 5, -3 to -5, and 3 to 5. And what you can see is that as soon as you require that there is a energy below threshold in one of the 2 ZDC, the one that is on the same side of the 0 neutron, well, you can start seeing that the average multiplicity of central barrel event decreases substantially. So we have actually studied this very carefully. To be honest, this is probably the most challenging part of the analysis. You know, we know how to reconstruct the 0 jets, but making sure that we had no contamination from hadronic was very, very important. Again, when you do J-psi, coherent production, this is a limited problem. But here, whenever you start looking at jets and heavy flavor, then the chances that you would get something from hadronic becomes sizable. And this is, of course, something that you have to be very careful in treating in systematic uncertainties, etc. So, this is what we could do if we could collect all the events. But again, one of the biggest problems is that CMS is designed for mostly for hadronic physics, and it has a level 1 bandwidth of around 100 kilohertz. This means, for those that are aware of some trigger strategy, that out of the initial 0 bias rate that can be in the order of 10 megahertz, we have to push down everything down to 100 kilohertz. Typically 50 kilohertz is taken by hadronic, at least at the beginning of the run. So we have to figure out a way to reduce the rate of the incoming rate, but without losing interesting events. And what we managed to do is to use ZDC as a trigger detector. So ZDC is again what triggers on a detector that detects the neutron producing the breakup. But ZDC was using CMS as a readout mode, as a readout detector, was never used for any level 1 algorithm. And there is a non-trivial problem with the ZDC is that it's very far from the detector. So even if you just calculate with the speed of light, you are getting very close to the threshold of the tolerance of the level 1 trigger system that has to take a decision with a buffer of some 100 nanosecond, but it cannot be microsecond level. So this was actually a pretty interesting challenge. So this was the first time that we could get the ZDC. And then we had to study way to trigger on very soft jets in CMS. And we actually managed to have a pretty reliable jet tagging for jet down to 8-10 GeV. That for CMS is pretty much some kind of not almost illegal thing to do. The second thing is that, of course, since we have now a very big problem, there is a program that is emerging, we had to start squeezing the data size overall. And this was actually something that was very successful. Every time we create a lot of problem to the PP communities because we are always the one that requires more HLT bandwidth. And then they complain, but then the year after they implement it also in PP. But they have a good way to blame the heavy ion people. So long story short, by putting the ZDC in trigger and having this UPC a photonuclear jet trigger, we could basically collect the entire statistics from about 10 GeV, 10-20 GeV jets. And in 2018, there were a few millions of UPC events. Now we could collect in the order of 10 millions of UPC photonuclear event in gamma P and gamma nucleus. This is how an event would look like, and you can see that this is not what we are used to see at the LHC. So there is, of course, a dijet. There is a very much boosted topology. Now, one might think that this is actually coming from the photon direction. Most of the time, such a topology is associated with a gluon coming from this side, because even if you select high energy photon, the maximum range of energy that a gluon could have is still higher, because of course you scan over from low energy up to 5 TeV, okay, in the extreme case of x equal to 1. Photon in general are lower. But the second good thing is that you have no underlying activity. So effectively, this is actually a very interesting playground if you want to do in vacuum physics of jet fragmentation without pileup or any sort of background. So it was actually, so we did this crazy data taking experience in September of 2023, and then in 2023 November we started taking the data, and quickly we could get our first result. So we started from the open charm because this is always the easiest thing. Jet reconstruction at low PT is a bit more complicated, and theoretical charms is very easy to be described. And this is a classic analysis. If you are in ALICE or in STAR, you know how to do the zero analysis. What I want to say is that there is basically no cut optimization here. There is very, very little background. And actually, the background that we are dealing with is mostly art background from heavy flavor decays. So the uncorrelated background is pretty negligible. Here, as you can see, we are paying the price that in ALICE we do not have PID. So there is this big swap component that would be K pi on pi K on, but can be actually modeled pretty well in Monte Carlo. And then, of course, now we have shown that we can measure this event. Now the question is that how can we change the X and Q square? And in this case, at least for charm, the picture is simple. So we have X of the gluon will be dependent in terms of scale from the PT of the D0. In reality, would be a PT of the charm quark. But this is our proxy. And then there is, of course, an exponential on the rapidity. And this is, of course, where the fact that we have a very large pseudo-rapidity acceptance help us a lot. You basically measure the analysis in PT and Y, and you map a different region of X and Q square. So, and then of course we did the analysis. So what is interesting to see is that this is even with just a very small amount of data, this is the first data taking that we have collected. So we were not super efficient in terms of bandwidth, but we are already a systematically dominated analysis. The uncertainty on the yields are in the order of few percent, even with these limited statistics. So the deal is really to understand Monte Carlo description, contamination, and et cetera, et cetera. So how the cross section look like? Well, this is a cross section of the charm as a function of the rapidity. And the first thing that you can see is that this is asymmetric. This is not the usual plot that we see at the LHC. What you can see is that this is a this is obtained only selecting event in which photon come from one side and the gluon come from the other. So it's a 0n(xn), so no neutron on one ZDC and at least one neutron in the other. And what you can see already is that, of course, the low PT has a larger yield, but there is an asymmetry because the photon has, on average, less energy than the gluon. So it's easier to find out a charm recoiling in the direction, toward the direction of the incoming photon. And of course, if I have to map this in X, well, this would be the low X region, okay? Because just like simple kinematic things, if a more energetic object comes here and drags the final state over there, then it means that the photon is more energetic, and you can see the yield is lower because, of course, it's less likely to get a high energy photon. What happens if we now swap the conditions? So we ask for a 0n(xn) event. Well, that is clear. There will be the distribution will be reversed. Okay. And one of the things that convinced us that we were doing the right thing is that we were obtaining a cross section that was fully compatible within few percent when looking at event where the photon was coming from the left and the gluon from the right, and vice versa. And you can imagine how dramatic is cross-checking this, but this was actually pretty well under control from the very first day. This is because I think CMS has a pretty good Monte Carlo description of, in terms of performance. It was not trivial to measure the zero at very forward rapidity. As you know, forward has a lot of material budget, so the multiple scattering is large. The efficiency will become slower. So it was actually the first analysis that exploited the very forward region in for such a way. What you can see is that the systematic uncertainty are still large, and I think I'm reasonably proud of it because we were conservative. So this is the first time that this signal was measured, and I think the right way to do is to be careful and to be conservative. Also, the Monte Carlo description, we relied on new Monte Carlo, so it's very recent that we have photonuclear production in a heavy ion environment. I think this can be pushed down substantially, but that's what we want. We felt confident in doing for the time being. What we have done, of course, is that once we have checked that the two measurements are consistent, that we combine them together because the agreement was indeed within the 1-2%. So now we had, of course, fantastic, we got a nice measurement, but there is one problem. Now we want to convert this nice measurement into some constraint in terms of X and Q square. And unfortunately, there were no calculation because this is indeed a new signal. So it's not photonuclear production of charm was measuring electron proton, but nothing that was available for the UPC environment. And okay, so this was a long story. It took about a year and a half, but I managed to convince some kind theorist to help me out with it. So we went to Fonelel Fortran code, which, okay, is an interesting experience, especially if you don't know Fortran. But we got the public version of Fortran, and then we had to figure out how to a public Fortran version of Fonelel. Fonelel is the most common low PT D0 next to leading order fixed order, next to leading order fixed law calculation. And we have tried to make it work for the UPC conditions. And the most, the first thing that you have to do here is, of course, you start from an electron-proton system. You have to reweight the photon energy distribution in order to match the one from UPC. And that's what we did. You also have to make sure that you have a proper PDF for the photons, right fragmentation function that, by the way, can be different from PP, etc., etc. Let me just show you. This is actually a comparison between the proton energy distribution in UPC and LLED. LLED gives you much more yield, but much less energy rich. You have to reweight everything in the Monte Carlo. So we have embedded the photon flux energy. And then we had to deal with a very problematic effect. The problematic effect is that when we measure photoproduction in UPC, we are selecting on the ZDC topologies. We are asking, for example, that there is a 0n and a xn. A funnel calculation doesn't know anything about ZDC. Okay? It's a purely inclusive photonuclear production. Something that took a lot of time. We had to learn how to deal with the fact that even in absence of a R scattering, when you have two nuclei that crosses each other, they can dissociate. There can be a soft photon exchange. What happens is that if you select event with 0n xn, well, if that nucleus dissociate independently of what is produced in the R scattering, then you would have a reduction of the event selection for photonuclear. So this is something that was preventing a lot of this measurement recently. We have worked a lot with theorists. There is an analogous measurement for DiGET from Atlas. So we have now a pretty solid way of correcting for what is called electromagnetic dissociation that was also cross-checked with data. It's a slightly technical discussion. I'm happy to follow up offline. But these were basically the two main elements that we had to figure out. The good thing is that we also Kachari, that was one of the authors of FONLL, joined the effort. So, and now we basically upgraded FONLL to what we call gamma FONLL, and it's basically an extension to any kind of UPC. We can do photonuclear collision from UPC LED, but we can also make prediction for a gamma proton collision. And now we spend an infinite amount of time making sure that our predictions were fully consistent with the one of Zeus from electron-proton collision. And of course, we are also ready to make a calculation for the electron-ion collider. At this point, it's just about changing the photon flux and the NPDF. And it's already implementing pretty much state-of-the-art of NPDF calculation. Okay, this went in parallel and took a lot of time, especially if you have never done UPC like I did. So I was learning from scratch. So, and then what we have done is to use it for making calculation, predictions. So actually this is 5 to 8. I don't know why I left 8 to 12, but this is our data compared to where we make a ratio with respect to theory using NPDF and using proton PDF. And the good thing that is not trivial is that, I mean, exclusive J-psi production have been trying for 15 years to have next to leading order calculation. We get it for free, almost for free. Okay, that took a bit of effort, but nothing compared to make a next to leading order calculation in CGC. And what is actually nice is that now we have a tool that gives you a X and Q square dependence. And for example, you can easily see when CGC calculation breaks down. And we can clearly see, you can see it even better here when we have a scan as a function of PT. CGC gets pretty well at low PT, and then it breaks up when you go to IPT, as it should be. But at least we have a observable that we can tune to see where it agrees and where it is, where it's not. So this is, of course, a first measurement. The hope is to substantially reduce the uncertainty. But what you can see is that if you compare the data with the proton and PDF, you can clearly see that there is a trend as a function of PT. And this calculation can go right away in an NPDF feed. This is what J-psi measurement cannot do, although they, of course, have potentially lower X range. So this was actually our first step toward having a broad program of jets and OpenAV flavor in the LED and in P-LED UPC. As you might imagine, an important PT is the low PT, because that is where we expect a saturation effect. And now we have started using doing more differential measurement. So this is an updated analysis from last fall, in which using still the same data set, because we didn't have more LED data, we have tried to dissect the Y dependence of the low PT. Now, there are a lot of caveats in this plot. This is a ratio done with respect to a theory calculation. So we cannot make draw any final conclusion. We cannot say, oh, we see a disagreement with respect to EPPS09 or PPS21. Statistical uncertainty and systematic uncertainty are right. But I think that what is important is that we are already at the stage where we can start putting some constraint. And of course, we are now working, doing a lot of work to improve the accuracy of the measurement. We have about 5 to 7 times more data. And we can also use, we also show that we can use a pixel PID in the very low PT region to reject pion contamination. So this is actually a work in progress that of course, we are hopefully getting there. I think that for a first round of measurement, I was actually pretty happy to see that. Now, in the last 10 minutes, I want to show you something that goes beyond the current measurement. And one interesting aspect that I mentioned before is that what UPC lacks is full control on the Q square or the transverse scale of the scattering, because we do not have the photon measurement. So one thing that we find interesting is to try to use basically full event reconstruction, for example, when you have tagged at D0, so that by looking at the final state, for example, the dijet, you can get closer to the kinematics and X and Q square of the scattering. So this is something that we are trying to explore now, both using dijet reconstruction, like jet reclustering technique, but also trying to do full event analysis once you have tagged the presence of a final state with an IPT jet or charm quark. So yeah, this brings me to pretty much my conclusion. So I try to present you some challenges. So we know very little about nuclear PDF, and in particular, what happens when we go to a very low X. And this is so far limited by the scarcity of high energy photon-nuclear data, and in particular, the fact that we do not have an electron-ion collider. But ultra-peripheral collision are something that is becoming really quantitative. So at the beginning, I think it was seen, oh, this is cool, we can see some photonuclear collision. But now we know how to handle this event much better, and the knowledge is increasing over time. So if I think about what we know about dissociation now with respect to 10 years ago, a lot of work from theorists, and not only experimental, is really a lot. And we are growing in terms of theoretical control, and I think that the refinement of the measurement is increasing really, really dramatically. And of course, I'm from CMS, but I really would like you to have a look at the very, very beautiful measurement that Atlas did of dijet in photonuclear. That's really something that paved the way also for the work that we are doing. So I think we really have to give credits to those our friends in Atlas for doing a very outstanding job in exploring this event. I also wanted to mention that this is a program that I think, involves, of course, many experimentalists, has a very strong program, STAR as well, Atlas as well, but it really takes us far because we are now at the stage in which our measurements are become accurate, and we have also control on the theoretical part of this program. And then we have big upgrades. And the first upgrade, at least from the side of CMS, is in run 4. We would have a basically brand new detector with much larger certainty. But you can see how easily and how well this program extends to the IC, of course, where we can effectively measure the same processes. So exactly the same processes. Bear in mind, if you look at photonuclear, even in electron-ion collider, you would just put an uppercut on the virtuality. You don't scan Q square from 0.5 to 0.7. So the process is really very similar. And I think the fact that we will have a very long overlap between EIC and LHC is something that makes things even more interesting. At MIT, we are working very hard on the pixel of EPIC as well. So but both from theory and experiment, we are learning from each other. A couple of things that we are already trying to do now. So I'm getting more and more interested in diffractive physics. First of all, I don't know how much you know about diffraction. I knew very little, I have to confess, but it's a very interesting type of process. You know, when there is an exchange without a colorless exchange like a pomeron. So this is a way to enhance sensitivity to very low X. So what we have done for this last oxygen run and proton oxygen, in addition to do the Charge Hadron Array that we are very proud of, is to start expanding the forward capability of CMS. This is a story. I was looking, we have a hole in CMS that go from 5 to the pseudo rapidity of the beam, so like 10 where the ZDC are. I was dramatically looking for some detector that we could place there. And at some point, someone told me, oh, actually, we had for a year in run 1, some forward shower counter that were put around the beam pipe, and they kind of cover the same pseudo rapidity. I was like, fine, where are they? They were in Turkey, in Istanbul. So we spoke to this our friend from Istanbul, and in PLAB we managed to put the first set on the proton side. So here the idea is that we want to get as much cover as possible in the forward region to be able to say, okay, is this a diffractive event? Is it a photonuclear? Are we still getting some contamination? So we managed to put it in, and also we managed to get the proton spectrometer on the proton going side. So this is really a detector that tags the trajectory of the proton. So if the event is diffractive, the proton is not broken, you can actually track the measurement. So long story short, in the last P oxygen run, we had the full blast detector, ZDC, forward counter, and PPS. And in oxygen, we had forward scintillator counter and ZDC, because we do not know what will happen yet at the PPS if it is in the beam of ion. We will try to figure out for next year. I was told that the PPS will be trashed, so maybe we just put it in the beam and we see what happens. I mean, worst case scenario will burn, I guess. I think that this is something that we can do now, and then run 4 for CMS is going to be very interesting, as well as for other experiments. At least we'll have focal, and we will have a ±4 tracker. These are predictions that I made with Anna about photonuclear coverage for UPC. We will have some PID, the good one, not the pixel one that we are struggling with. And hopefully, until last week, we had also a plan for having a ZDC. Now, DOE seems to have different ideas, but maybe we'll try to find the money somewhere else. And I think it would be very important to keep on having the full coverage with this forward scintillator. By doing this, we will be the only 4-pi experiment at the LHC that has this kind of capability and proton tagging capability. So as you all know, long-range program of US is EIC. I don't think that I need to convince you that we are dealing with the same physics. These are exactly the same processes. I want to stress that it would be, while we will have lower, less powerful OX coverage, having full constraint on the Q square of the photon of the electrons, and of course, of the photon through the electron tagging, gives us very interesting prospect. I think that's something that I'm still very puzzled by. We talk a lot about hadronization in the medium, but effectively we do not know how much time hadrons takes to be formed. And when I was discussing this with Mark Strickman, it was telling me, yeah, of course, we have been discussing with Bjorken for ages, and we never figured it out. He tried to explain me how to calculate. I didn't understand anything, but I understood that this is still an open question. And if I think about it, when we talk about hadronization in hot QCD, well, it would be nice to know how much it takes in the vacuum, because that seems to be a pretty interesting question. And this is something that I think will be possible and beautiful to have at the LHC while we keep on taking our beloved LHC data. And that's all. Thanks a lot for your attention.
I have a quick question. On when you make the measurements for the digits, you have the C and C bar pair. Could that technically be anything else? Like you mentioned the phi, I guess. But then, is there a reason why you focused on heavy flavor?
So the reason why we focus on heavy flavor is because for heavy flavor, calculation are very, very simple. So I would not be able to get next to leading order calculation for phi right away. What one can also try to do is to make an inclusive measurement for j psi, for example. But I think that the long story short is that with CERN you can trace the final state, and then also you have next to leading order expansion that goes to 0, which is not the case for light flavor. That's pretty much the
Fair enough. And then just one more. When you for these types of comparisons to the EIC, but the EIC will be polarized, right? Do you think that will change? Did now make it more complicated?
So for photonuclear events, this doesn't really matter. So if you do spin physics, of course, that is a big advantage, which is I think what also is a limit of UPC physics. I mean, it's very exciting, but I think one has to be honest. There are things that we can do and things that we cannot do.
Yeah.
But for photonuclear, I think the setting would be very, very similar. And I think we can learn a lot between now and then. For example, one aspect that is still unclear to me is that you know, in electron proton hadronization doesn't get too complicated. But what we have seen already from UPC measurement from Atlas, for example, there is a very sizable hadron modification in photonuclear as well. Depending on what would be the ratio of resolved versus non-resolved in EIC, this could even get worse, because the more resolved you have, when you have a resolved photon scattering, it's like scattering a pion with a nucleus. So you would have a final state effect where you see flow. So I think that there is much to learn from it, keeping in mind what you can do and what you cannot.
John might have a comment on the question.
John, we cannot hear you.
How about now?
Yes.
Okay. So, yeah, ciao Gian Michele. Come stai?
Bene, bene.
Grazie per
All good, yes.
la visita oggi e mi dispiace di non essere presente lì. So, but yeah, I was going to ask you about, and I'm sorry, you know, I'd like to just speak with you sometime. I was going to ask you about beauty and UPC, and given all your statistics, although you're limited, when you were talking about the CC bar dijets, you're limited by systematics, it seems. Again, I'm talking about heavy ions UPC. What do you think you can do with the BB bars, and what can you learn from it?
So for these, I think our current limitation is level 1 bandwidth. So we could the statistics available is probably a factor 400-500 at low PT. Sorry, let me rephrase it. At IPT we are taking all what was delivered pretty much because we have triggered events. At low PT we are looking at zero ZDC or events. So there we are limited by bandwidth. So in a way, there we have room for improving it if we can improve our level and capability, or detectors that are untriggered, like Alice could do way better. For the beauty, I actually did, we ran the calculation last week, and fully reconstructed B are statistically limited. So we would get, I think we would need a factor 10, we would need 10-20 inverse nanobarn of data to get a good measurement by using dimuon events. If we would look at fully reconstructed Bs in the hadronic decay channel, that would be already probably doable. if you instead are thinking about tagged jets, this is something that we can do already now. And because all these jets are quark jets at the end. And we have been trying to make a BDT-based tagging of the jets to have the charm and the beauty fraction. But I would say that my answer is twofold. If we are thinking about fully reconstructed B hadrons, we are limited by statistics to a large extent. If we're looking at jets, what we have to do is that we have to learn how to do tagging at lower peaking.
Okay, thanks. And maybe one more question. On this timescale of hadronization is very interesting. I know Bjorken used to talk about it a lot, and no one in high energy cared, frankly. You know, it just happens. And so I was wondering, it looks to me like you're talking about measuring it at EIC, for example, by looking at the virtuality, the dependence on virtuality somehow.
Yes, yeah, exactly. So my thought, this diagram was biased by the work that I've done with Urs about gluon splitting. So in that case, I mean, I got slightly obsessed by formation time recently. But the picture would be indeed to use the photon virtuality to set the time, the formation time of the CC bar, and basically do a scan. Or I mean, CC bar because would be the cleanest way to do it. But that's exactly what I had in mind. So if one could look at quote unquote time dependence through the electron and seeing how for example, the broadening between the CC bar as a function of the photon virtuality or something along this line.
And does it help to, if you were also able to measure other channels like BB bar and compare, or does that matter?
It would of course, because you would have, I mean, I guess that if we're thinking about some crowning effect, mass would definitely enter. Yes, I think that this would be like effectively like a flavor dependence of cold nuclear matter in a way, with the advantage that if I can measure a CC bar and BB bar final state, then I would also have a broadening effect. So if we think about what happens in the hot nuclear matter, we see that the broadening effect between CC bar and BB bar changes substantially, is of course very reasonably different. And I don't doubt that something similar would happen in cold nuclear matter.
Okay, va bene, grazie.
Thank you.
Thanks for a great talk. I had a follow-up questions on the BB bar. So I guess you said you would need a lot more statistics. Are you more limited in just the B meson or B meson production, or like BB bar production, or just the ability to reconstruct?
No, I think that if we want to measure fully reconstructed Bs, then you are beaten by the branching ratio, and also by the fact that we do it typically on time muon channel. And for those, we have level 1 triggers that are fully amply scaled. But they prevent you from going to very low, because the muons will not reach the outer layer. So instead, for the jet, is more like a technological problem. So what we are in CMS now, all these measurements are done with using a very complicated network that I understand up to a certain point. So I would like to first be able to have a tagger that is optimized and is under control. But the interest is that here you do not have any underlying event. So effectively, all your digits, very, very high fraction of the digits are heavy flavor. Light flavor contamination is lower, and there is no pileup whatsoever. For us, it's a matter of triggering, having no biases, and learning how to deal with the low occupancy, low multiplicity jets.
And as you tune up the precision both in statistics and systematics, do you think there might be any way to access the B through its D meson decay channels?
Yeah,
Like,
this is already something that we do. We measure the non-prompt fraction in the D meson analysis. Of course, if we could do it with a fully reconstructed D, it would be better. Probably for CMS, if we do not want, if we are focusing intermediate region, probably non-prompt GPSI is easier. Yeah, so it's something that can be tuned. And, yeah, for tagging tagging a BB bar jet is very simple. There is also one thing to consider. Once you tag one jet, the other one is almost tagged, because gluon splitting is super I mean, having a next to leading order correction becomes energetically very complicated. So once you tag a D event, you are almost sure that the other one is a charm, anti-charm jet as well.
Any more questions?
Yeah. I think I have a really fundamental misunderstanding. I thought this was a gluon, no?
Sorry?
When the Ds that you were measuring earlier on, isn't this a photon scattering off of a gluon?
Yes, so this is EIC.
But if I go back to your
Yeah.
CMS measurement,
Yes.
then now you're talking about jets, and that's where I started to think I missed something really. So, like,
So
if you want to relate this to exactly, so are these back to back?
yes. These are back to back, but not at y equal to 0.
Right.
This is a leading order. I mean, if this was a LHC, this would be gluon, gluon. This would be glue to CC-pi. This would be the leading order description, the leading order process of charm production. And since the two quark gluons have on average the same energy, they will be the central barrel. Here, the difference is that the energy of the photon would be on average lower, and you would have an asymmetry system, but the diagram at leading order is exactly the same.
Ah, okay. Okay, good to know. So, and then you're mentioning jets, but you've related the D to the Q squared. Is this really not the Q squared then? If you're now talking about finding jets around this D?
So if I have an inclusive measurement like we do in Fonedel, the scale that enters when you have to pick up a NPDF value, you would the scale that Fonedel uses is TT square of charm plus mass square of charm. So that is the scale. However, this is introduces a pretty broad dependence with the actual Q square. First of all, because you are measuring the heavy flavor hadron production in the jet. So there is a fragmentation function that enters in the game.
I thought you required low multiplicity. I guess maybe that's the bit where what you mean by low multiplicity and what I thought, yes, okay, there's a fragmentation, but basically the D is really high Z. So it's, but
the
not
D
necessarily.
is not necessarily IZ. So what
I thought you were requiring this by saying there's a gap and not much at mid rapidity, but the not much at mid rapidity is
okay.
not
So what I require is so I measure the D in the central barrel only. What we require here is that there is a rapidity gap, but the rapidity gap is tuned in order to reject the hadronic contamination from lead hadronic collision. So this is actually a good question, because when the photon is very energetic, the jet gets forward. So one of the things that we had to figure out very carefully is that we were not vetoing the shower of the D with the rapidity gap. But since we have now still a sizable, if we use a D that goes up to 2 in rapidity, the spill out of the shower that goes at rapidity 3.2 is very low. However, in run power, it would be a disaster, because we would have a very forward D that would enter in the gap. But the gap at the moment does not require an exclusivity in the final state of the dijet. It's purely related to the rejection of the hadronic. Now, if we want to measure diffracted jets, that's what I'm getting into. That's a very different story instead. If you want to do exclusive dye-jet measurement, then it's more complicated.
Thanks.
Questions? Okay, then let's thank the
Thanks a
speaker.
lot.